So then we want to also provide another kind of modeling, because that might be tight in some areas. And so we want to add probability. And one use case we're going to see from today, and that is just an introduction, so I'm keeping that light. From today to the next part is going to be how I could use probability to mimic not the probability of action, but to try to reflect, for example, the strength of the player. So you might encode with a probabilistical value how much confident you are that the player is strong, and that might resolve into the success of the action itself. Therefore, that might be encoded inside your state machine, if any. And definitely we're going to provide like realistic games even in this scenario, even better in this scenario, I might say. So we're going to see initially something very simplistic, like simplified tennis, Pong. So how to encode like a state machine with probabilities if you have just Pong. That might be hard if you're starting to think about that. Do I need to consider all the possible keystrokes to reach the ball? That might be wrong, might be hard to do, and it's going to bring you nowhere, because you need also to instruct how to do the keystrokes, and then you might need to learn to do that, and then you need to reach the action, which on the other hand is going to be better. Okay, I want to do this, then you're just instructing the machine how to reach the point, or how not to reach the point if you want to. And then you're going to see also something different, which is going to be more relevant, how then you could use probabilities to mimic and determine the time it would take a game for progression. So you have something like snakes and ladders. So even in there you have a probabilistical game where you are running a die, and depending whether you hit a snake or a ladder, you'll be progressing or going back to the game. So the question is, if you're providing power-ups or slowdowns, how much will affect the progression of the game? And that will provide like an interesting insight on how to model games from a mechanic point of view, how you should try to extend or decrease your game. And if you're not doing that for the coursework, it's just going to be relevant whenever you're going to do your work and your job and you need to model the game, for example, or even in the dissertation if you want. So some of the students, for example, they were exploiting these techniques. So they were trying to model similarly as we're going to see now, like a state machine for Monopoly game. Then the rolling of a die is actually reflecting the hitting one specific cell, and then you want to use like probability theory and determining which is actually going to be the best action or the best land part to buy. So that might be used also for this kind of stuff. And definitely then from the player point of view, you want to get what is actually going to be the probability of winning, or how much time do you need to take in order to win the game or to finish the game. And those are actually part 1 and 2 down below. So just for providing that, so what is actually the main purpose of that? So the main purpose is that you want to provide somehow game balance. So as I was mentioning before, if you have like a stochastic behavior, you might also tweak the probability values to change also the behavior of your opponent, so to prefer a more friendly to a more attacking move. But that is actually if you're assuming that you have a non-player character. But that could also be reflected on how you're setting up your level, your game, and how changing the distributions of obstacles and power-ups will actually provide different game experiences. With the idea that obstacles should be never unfair. So you want to detect that before providing the game to an alpha tester or a beta tester. So you want to have like a rationale how the game is going to be. So one way to do that is actually using statistical analysis. So you are knowing if you're going to take a power-up or a slowdown going back, and then you know that you have a certain probability of reaching a specific area, and then depending on that, then you're getting how many turns are required to reach the game. So then the idea is to do like post-mortem analysis and try to, so that is actually one way. You're having your alpha beta testers that are playing the game, they know what they were experiencing, you're having the logs and then you're determining that, or as I was mentioning, you're trying to do that before the game goes into production. So that's why you need more like of a modeling state or anything of the like. And then the thing that is actually in the first line is the thing that I wanted to say. So if you are not able to summarize all the features making a player stronger than another, because it's actually too complicated and you cannot go inside the brain of a player, then you could mimic the strength of a player like a probability value, even though it's simplistic, but they sometimes would do. And because then you know that the game should be mainly influenced by the skills that you have on the player itself. And those, as I was mentioning, may be hard to assess correctly, so that's why you're summarizing those as a probabilistical value. So that's why then we want to model the Pong game, as I was mentioning before, so in a way which is very straightforward. Am I progressing? Am I hitting the ball? Am I winning? Am I not winning? What does it happen? So let's do a very simple game, because you might do like a mini triple game, but it might be very complicated to model. So let's start with basics, just to allow you to wrap your head around that. So in here is just also a very extreme simplification of a tennis game, where you have also rounds. You might think of the round is you have the ball bouncing back and forth, and each round is whether the two players are able to hit the ball. So you are still within the round. And so, as you also have in tennis, one of the two players who's going to start first is going to be randomly picked before beginning the game. And in here, just simplistically, you might have 4 states for modeling this game. So you have one state where the current player is actually its turn, and that is simplified by, for example, the ball being on the receiving side from its end. And then you know that is going to be the other opponent's turn whenever the ball is going to reach the other side of the field. So that might be 2 states, under which then you have like a probability value subsuming the ability of the player on taking the ball and sending that in the adversary field. And then you have between these 2 states a probability value determining the strength of the 2 players. So you have P and Q, and they are representing the expertise. And then you have also something else, as I was mentioning before, which is actually the final states. I might reach 2 final states. One is actually the state where one of the players is winning and the other one is losing, and the other state is actually the vice versa. And so also in this assumption, and then I will stop because you only have 1 minute. From where I stopped last time, do you have any questions regarding to what I taught or regarding the coursework? And or the exam? No question? So either everything is completely clear or you have a lot of doubt. One of the two. So let's hope for the first one, that everything is clear. But anyway. So the part where we stopped last time was actually from this graph. So just to provide a brief recap on how we arrived in here. We arrived in here with the major purpose of trying to model, like using a state machine, so to speak, the behavior of 2 players. So that is actually something rather common, even if you're using like, how do you say? You didn't do that, and there is no module here in Newcastle University, but if you're doing like theory of concurrent systems, then you could provide like algebraic representation of processes, which combination is just one state machine, so to speak. So as a specific case of state machine, but anyway. So you could always model the behavior of two or more components with just one state machine. So that's what it is. And in here, the thing that we're trying to do is also to assess. So the target that we're aiming towards are these initial research questions that we posed at the very beginning of the slides, which is establishing which is going to be the probability for one player of ending the game in a given amount of turns, and establishing what should be like the average number of turns required for ending the game. So the idea is either you're guessing and you're tossing a coin, or you're using math for establishing something. Because everything that is actually going to be learning based is just learning from experience, and in here, the thing that we're trying to say is modeling the problem, and out of the model that we are providing, which is actually a simplification of reality as always, then we're trying to get this kind of estimates. So the thing that you have in here is whatever is actually a graph could also be modeled by a transition matrix, which is actually the thing down below, where if you have like no edge connecting the states, then you have a zero within the matrix, meaning that there is no probability of transiting from state to state. And otherwise, the thing that you're having is each state describes a configuration of your environment where you're at. So just for recapping, in this description, we're always starting from initial state, because I know that usually even in game design you're just providing a state machine, but it's very important to say what is the initial state. So that is actually always pointed by an arrow, so I always start from this state, S. From there I'm tossing a coin, and I have like 50-50 chances of one player or the other starting playing, so you have 0.5, 0.5, and therefore you have like two other states, x1 and x2, which are the players that are starting to play. And similarly, so you need to decipher this matrix where the columns are the source state and, the name of the rows are the source states and the name of the columns are the target state. And that is actually paired on top with the graph. And there will be a specific purpose where we're going to use like matrix representation, because math is going to treat matrices better than a usual graph. And then, as we were saying at the very beginning, then you are encoding the problem into a number set of states, into the initial configuration, which in our scenario is just a state we're starting from, and actions and transition. So the action is the thing triggering the change from state to state, if any. And you are not planning problems like proper like PDDL domains, but so where you have like preconditions that have to be met in order to trigger the transition. In here, we're just assuming that if you want to do an action, it's because you can, or because you're doing that nevertheless. And so if P1 serves, then you have like a transition probability of starting, transitioning there from state S to state X1. And if P1 responds, then it's actually the turn of player 1 responding to player 2, then it will win, potentially, and that is actually the strength with probability P. On the other hand, also the other player could respond, and that will come with another probability, which is actually reflecting the strength of the other opponent, which is Q, therefore is actually making the transition of the ball from one field to the other. So that is actually what the transition is describing. And then eventually you might get the ball towards one end of the field, and the other player doesn't catch it. And so, symmetrically, then the probability of not catching the ball is 1 minus P, which is actually the probability summarizing in a very straightforward way the strength of the player. So you have like 1 minus P, and then you know that the other player, 2, is actually winning. And then you have a goal condition, which is different from the play of doors and the configurations, which is just I'm reaching one of the two states. And that will actually provide me the description of the Pong game. So then, any question before we shifting towards another game, just to provide another use case scenario? So just to show you that the way we're modeling the problem is actually the same independently from the game, for this kind of simplistic games, then we're going also to show that we could model in the same way also a game where the player is playing against the environment. So in here you have one-person games. In this scenario, that is actually very common in robotics, even if you have like a robot that needs to crawl the environment and decide where to go. So even though you're saying, oh, that is actually a bit pointless, you have only one agent, but most of the real life use case scenario, you only have one agent interacting with the world. So even though it might seem too simplistic for you, it's actually very realistic and very much suited. It still comes with a real set of problems, and there is still ongoing research because then we have multiple facets for describing the kind of interactions. And usually these kind of approaches, which are logical based, are the most used one because you have more control on the environment or on the things that you want to do. So the thing that we're doing is to say that still in this scenario we have one agent, and we're considering, as in the previous sense, decisions that make effects. So we're not considering any kind of decision which is inside the internal mental plan of the agent, but just for modeling purposes, we are considering actions that are providing like a state change on the world. Albeit that might be a bit too unrealistic, because if you're piling up a set of decisions, then those, and you have memory, then you could also change your decision eventually. But in here we are just assuming memory-less games. So that's why we're only interested in actions that have an immediate effect on the world itself. And in this scenario, then we don't have a conscious opponent, and still we know that the agent might progress or not within the game. So just to provide a use case scenario, we have this kind of game, which is actually very common. At least it used to be in the past, of snakes and ladders. So in this scenario, you always have probabilities. Why? Because you have like a player starting from the very beginning of the board, for example, from the lowest cell in here, bottom right, and then the aim of the player is actually reaching the final state, which is actually on the bottom right corner, and then you are just defining the environment. Not quite, because then you need also to model that you have 100 states from the beginning to the end, and then you have everything. Then the other thing that you need to model in this scenario are the transitions or the actions. Or better, you need to model the actions and the transitions associated with them. So in this kind of game, the thing that you have is like all the actions that the player is doing is just rolling a die, and given the outcome, is actually moving and transitioning from one cell to the other, given the probability of the outcome, which is always 1/6 if the die is not rigged. And then depending on that, then you have like actually three possibilities. Either I'm in a free cell, and then I have to do nothing at all, it's just stay there, or I land to the bottom end of a ladder, or at the top end of the stripe or of a snake. And then in this scenario, then I'm not only transiting towards this cell, but I'm also moving towards the direction pointed by the object. So the thing that I'm doing is if I'm reaching like the bottom of this ladder, then because I have like a probability of reaching this, the third cell in over 1/6, then I'm not actually providing a direct link between this cell and this other, rather than providing 1/6 of probability towards the upper end of a ladder. And similarly, if I'm taking the upper end, eventually I'm reaching the upper end of the stripe or of a snake, then that should not be definitely one modeling my problem, my final state. Rather, the final state should be the bottom end of a snake. So the thing that this game is actually providing, modeling, from the modeling perspective, is that you have two scenarios. One of speed up and power up, which is actually allowing you to efficiently navigate the game, and the other one restraining yourself and the player and actually going back. And so, why is that important? Because then it actually depends on how you are placing the ladders and how you're placing the snakes, and that will change drastically, as we're going to see, the experience of the games in numbers of turns that are required to finish the game, and in terms of probability of winning. So even in this scenario, we are just modeling, as I was mentioning before, memoryless games, because all the actions that I did in the past are not reflecting, as a consequence, the action that I'm doing the next step, and all that matters is just the current state configuration. And the way that I'm progressing the game is just rolling the die. So if you did like probability theory, but there is no module for probability theory here, then you have some, so that's why we're using like this Markov chain for modeling this kind of problem, actually because you have no memory information and then you're just progressing within that. So also please remember that a lot of things could be modeled in a memoryless way. One thing is actually modeling the arrival of packets to a server, or like you have birth and death processes, which are just not all expressing the growth rate of the population, but for example, could also model, you have a queue to in order to go to a gas pipe, for example, and that could also be modeled by a growth and death rate processor, because the growth is just how much the cars will pile up, and the death is actually how many cars are going away from the pipe. So a lot of real problems could be modeled in a memoryless way. And so the main thing is that now you have a probability which is not reflecting as before the chance or the strength of the player, but this is actually pure chance, because that is completely embedded by the roll of a die. So you see probability could be used to model different things depending on the aim of your modeling. So in here, I'm just providing like the mathematics of the thing that I was saying verbosely before. So if you're not having like snakes and ladders, then the only thing that you have are actions. The only actions that you have, which are actually the same also when you have snake and ladders, are the outcome of a roll of a die, which is actually either 1, 2, 3, 4, 5, or 6. And then all of those will have like a probability of 1/6, because by assuming that the die is not rigged. And then you are just providing the same probability of reaching the next cell, and you are only considering transition from the cell I towards the cell I plus j, where j is between 1 and 6. And that is very straightforward. So you just provide like something resembling like a diagonal on matrix with some changes, by the way, a skewed diagonal. But if you then need to model that also with snakes and ladders, then you need to add another probability value and remove the actual probability value when landing. Anyway, as usual, I'm providing that always mathematically, but you also have the code. So if you're going to the code base and you're looking for, no, not this one, classes, let's do like that. And then you're using, where was it? So in here, you have like the modeling of a Pong game, as we were seeing before. And in this scenario, definitely we are modeling like this graph, like with a list of transitions. In here, the thing that you're having, let me increase the font. You're creating like a discrete time Markov chain in the previous problem, and they're just providing like a list of transitions. So you're transiting from state 0 to state 1 with a given amount of probability, and then when initializing the problem, I'm deciding which is actually the strength of a player 1 and the strength of a player 2 by initializing the variable p's and q's. And in there, I'm just assuming that the final states are the states where one of the two players wins, and the initial state is the initial state where I'm starting to toss a coin in order to decide who's going to win. And that will create like a new discrete time Markov chain where 5 that you have in here is just the total amount of states that you have. So that is actually for one class. And then we're going to use those classes by computing something. And there, in Snakes and Ladders, you have the same code, but for setting up the problem. So as I'm always saying, all the things that I'm describing in slides have an associated code. So if you're not trusting the theory, you could run the code and double check what I'm saying in class. And in here is actually going to do the same, but in order to be like more straightforward, in order to set up things, I'm like using an external library for, how do you say, for using matrices. And so that's, but the MathNet library is actually added as a C project dependency. So when you're opening that as a Visual Studio should automatically download that and add that as a dependency. And then the thing that you're saying in there is basically setting up the transition probability in the normal cases, and then I'm determining in some other scenarios what to do if you have either a snake or a ladder. And then I'm determining that given the parameters that I'm having. So you have in here the snakes and the ladders. So the only thing that you're doing in the code base is providing the starting point and the end point for each of those. And then depending on those, I'm basically determining how to make the transition. So, and the snakes and the ladders are just meant to be used towards the direction. So are just mnemonic, but basically code-wise they're acting the same. So one is actually just moving forward and the other one is moving backwards. So semantically in the code they are the same. And in here there are just some subtleties, like for example, if I'm in a cell which is 97 and my roll of the die is actually 6, then I'm not going to be in a cell which is greater than 100, I'm just exiting the game. And so I'm squashing up all the probabilities. For example, if I'm in the cell 99, then I'm almost certain, if you don't have a snake bringing me down in one step, to actually continue the game. So I'm just adding up and summing up the probabilities so to finalize the game itself. So before then, we're going to show the mathematics behind the computation of the number of the turns required to finish the game or for winning the game. Do you have questions regarding the code and how that was set up, or the mathematical setup of the two problems? Good. Okay. So then we have something. So this is actually an important part of the slides. Okay. You might have questions on all this part of the slides. So even though for you it's actually merely theoretical, but I'm going to ask questions about that. And the kind of questions, so you should have like a facsimile of exam online for 3232 from the previous year. And you have like questions with solutions on Canvas. So you could also double check what you might expect from the exam in there. So in here, we want to focus on one of the two problems that we were describing before, which is just the number of turns required to reach one of the two goal states. So in here, the sense of goal is very generic, and it's just saying whenever the computation is going to stop, independently from who is winning the game. So we can prove that this reduces to solving the following linear equation. So as also a reminder from all the things that I was mentioning before, when I say we can prove that, then I'm not requiring you do the proof that is obvious. So, and then I'm not even asking you to remember by heart all of the formula in the exam. I'm just requiring you to remind the concept behind it, and that is more than enough. Then if you provide like the formula, that is great, but it's just like a mnemonic exercise. It's not an understanding exercise. So someone could also trick and just provide the whole formula, but not understanding what the formula means. So I want to know if you understand what this formula means, for example. So, and the same kind of setup is going to be used also in reinforcement learning for training the insistence value and determining the policy. So that's why all these concepts are related to each other, and that's why I'm introducing this kind of mathematical gibberish before introducing reinforcement learning. Okay. So in order to remember, so the thing that I want to achieve is actually the average number of turns required to reach the final state. So how am I doing that? So intuitively, when I reach the goal, then I finished computing any kind of step. So if you're thinking about backwards, then, and you're decrementing the counter, when you reach the final state, then you reach 0. So that's why for each goal I have a variable xi, so you do that, which is 0. Otherwise, then the thing that I'm doing potentially is I'm waiting, given the transition probability Tij, where T is actually the transition matrix, the value that I'm receiving from the other node. And then eventually I will have a state which is going to be the initial state, which is just going to receive all the ingoing values. So, but solving that using like symbolic computation is actually fairly not difficult for a computer, but they need to do some kind of reworking. So you could just pre-prepare the meal for the computer and actually say, okay, that is actually just a linear problem, and that actually boils down to solving a linear system, AX equals B. If you don't know what a linear system is, I'm also going to explain that to you, but you should be familiar, still from high school, which is, I have like a matrix A, which is just in this scenario a square matrix, but that is not necessarily squared. And then I have like a vector B of state configuration. So in there, I want to say, I want to move backwards to another state, so that's why I'm having -1 intuitively. And then when I reach a goal state, I want to stop because I finished the game. So that's why the goal state configuration is actually a vector B of all the state values. And then I'm just determining how to transit from state to state. And I provide, and then that is actually a rewriting of the transition matrix. So that is actually the idea. So the idea is that you are doing like a random walk, and so that is the thing that it's trying to say. So that is actually another thing. You are not necessarily required to do like Monte Carlo sampling for knowing problems. Sometimes you're just solving like a linear system, and then you have an exact answer, and not a sampled one. So, but if you're doing like, what is called, if you're doing like random walks on a graph, then it's actually like, I'm start one possible outcome of a game, which is actually starting from a state, and then I want to reach a goal, and then it will take some given amount of time. Then the next time I'm choosing another path, and then I'm considering all the turns that are going to be different between each other, allegedly, and then I'm just averaging out the time that is actually required to transit the matrix. So that is the main intuition behind this system. So even in there, you have in the code base, where was it? That you have compute average hitting times. So associated to deterministic time DTTM, so where is it? The discrete time Markov chain, you have already implemented this method, which is compute average hitting times. So given the matrix configuration, I'm obtaining the sparse vector B, the sparse matrix A. So if you don't know what sparse means, it means that I'm avoiding allocating memory for cells that are zero. Basically, that's what it means. And then just I'm using a lambda functions in here to determine how to initialize each configuration of a matrix and of a vector. And then I'm just solving the system. So the thing that I want to have, given the A and the B, I want to obtain the value of another vector, which is actually the X vector that you've seen before. And then I want to get actually a pair where I have like the ID of a state and the value associated to that. And then the thing that will compute at the output is for each state, under the assumption that the computation is going to start from this state, then the average time for finishing the game. So that's why intuitively in the goal state you have 0, because what is actually the time required for reach the state where you're always at 0, because you do not need to do any kind of transition, and each transition has a cost of 1, and the cost of 1 is actually averaged out by the weight. So then you have like a probability of transiting from one state to the other, and so that gives you the number of turns, where each turn is exactly equal to the same one. And that is actually the thing that is computing. So you see, I'm not requiring you to know how to solve a linear system. In here, there is actually a library doing that. If you're interested, you have like numerical linear solvers and the definition, but we're not doing like a module on linear programming problems or optimization. So, but the interesting part is actually the outcome of this. So you could also play with the code base and change the configuration, removing the snakes and ladders, adding just the ladders, and doing that. And by doing this, you will see that the number of turns required, average number of turns required to win the game, so reach the final state for the snakes and ladders problem, will change drastically. So without anything else, so you're just taking like 29 turns, which is not, I'm not taking all the steps for finalizing the game, because I could, allegedly, I have like the best case scenario where I have all 6, and then I have like the worst case scenario where I have all 1s, so I'm taking 100, and then I'm averaging out probabilistically all these times, basically. And then if you're doing the math, that is actually the thing that you're taking nearly 29 turns, which some values of decimals which are just the outcome of rounding up the number of turns, because that just entails the time. But if you're just adding the ladders, as you might expect, and you have a lot of ladders, as in this scenario, then you are reducing significantly the duration of the game. So you see that also has an effect on the gameplay experience of the player. And if you have only snakes, so if you only have possibilities going back, then you're having like 46 turns. And you could also have possibilities where potentially the game will never finish. So you might be very unlucky and the game will never finish at all. So even when I was plotting the results, then you need to remember, but in some times you have like numerical cancellation and some decimal might be very, very, very small, so you need to stop, otherwise you will get the probability distribution function for all the possible outcomes in some other plots that we're going to see next. In this scenario, I'm just counting the number of steps, so that is not a problem. But this kind of might become to the detriment of the user experience. So in order to have a more balanced game, the thing that I could also do is to add ladders back. So what does this kind of outcome suggest? That from the mathematical standpoint, I might have parts of the game mechanics or the logic of the game that might advance or fasten up the pace of the game, or some other parts that might slow down the game experience. And if you're not certain of what is happening, the intuition is to gradually add up or remove strategies up until you find the optimal solution. And you might, also given the game configuration, you might also notice that the game will never finish, and so you have like plus infinity or something like that as the number of turns for reaching the game. So in this scenario, it's going to be better to try to change the game policy and to structure the game in such a way that you're allowing the player to win. And what does it happen with Pong? In Pong, we could also do something parametric. In here is actually something where the linear programmers are not going to help you, but you need to use symbolic reasoners or symbolic manipulation algorithms. Like, for example, one example is Wolfram Alpha, but you have also Sage from Open Software, which is actually the same. So if you're setting up the equation and you parameterize that by P and Q, then you obtain like the distribution that you're seeing at the very below. So the thing that you could also assess is how much time it will take for the game to finish, dependently on the strength of the player. And in here you will say, okay, but well, it's obvious. If the strength of a player is very near to 1, like to these other extremes of P and Q, then I'm expecting that they're going to be I'm going to take like a huge amount of time for winning the game, and potentially if I have like robots under assumption or like oracles that are always knowing what to do in order to win the game, then you have like a plus infinity number of turns, so the game will never finish. Because allegedly, if the probability both of P and Q is actually equal to 1, then I will never have the edges from x2 towards w1, and they will never have the edge from x1 towards w2. So they will always stay in the loop, and I will never reach the final states. So as a consequence, the average number of turns for reaching either of the final states will be completely plus infinity. And as you see, I have no notion of the final state but the only thing that I'm interested in is the number of turns required for winning the game from the initial state, which is x of s. So you have this kind of equation on the top, and then you'd see that if you have one player which is going to be very strong, then and the other one which is very weak, still is increasing a bit the number of turns, but not too much. And still you have that the minimum amount of turns that are required for winning the game is actually 2. Because in the worst case scenario, you're tossing the coin, so this is considered as 1 turn. And then the other opponent will actually do something. And then the other opponent, under the assumption that is not pushing the ball towards his own floor. So I'm assuming that, like in Pong, is always able to push the ball to the other side. And in this assumption, then the other opponent is not able to catch. For example, the ball is always stuck in one end, or always does the completely wrong decision, and so the ball will go in the other part, and the other opponent will not able to catch it. So that is going to be the second action, and after that, the game is finished. So that's why the minimum amount of turns is actually 2. Otherwise, you have in-between possibilities that are averaged out by the probability of P and Q. So before we change to another mathematical setup, which is probability of winning, which is different from the other one was just probability of finishing the game. Do you have questions related to this part so far? For the average hitting time? Yes?
What does the transition matrix represent here? Is it a direction which is scaled by the roll of the dice, for instance, or is it like a global state representation?
It's a global state representation, which in the game of Snakes and Ladders actually represents the transition from one state to the other. So that will be clearer in the code base because actually I'm doing the iteration between 0 and 100. But in here on the slides mathematically, then there is actually this kind of parallelism. Let's see in here. So whatever is the transition of a graph, if you're accustomed to see transitions in a graph way, then, and you have a value associated with that, then that will correspond to a cell value within the matrix. And depending on the setup and depending on what you want to formalize, then it will be either, as you were pointing out, it has just a game of the player against the environment, where everything is determined by the roll of a die, then the probability is actually just 1/6, potentially, and that is just the probability for transiting from one state to the other. And this scenario is reflecting something different, which is the probability of winning or the probability of being in a given configuration. So if I'm starting the game, either one of the two players will play. So the two states are actually reflecting which player is now playing the game, which is actually the turn of a player. And the two other states are actually reflecting, as I was mentioning last week, who is winning the game. And then the transition is just the action. Does the player catch the ball in the Pong game or not? So if it is catching the ball, then you have a transition from one player to the other, from x1 to x2, because x1 serves and as a consequence responds, and it is actually responding to x2. Or if it is not able to respond, it doesn't catch the ball, then the other player is actually going to win. So then it actually depends on what you want to model. So that's why I have two use case scenarios. I know that they might seem confusing, but just to show that you could model two different kind of things. Either complete chance, if you want, but also both complete chance, as you have on top, because you have like you have 50-50 probability of one of the two players starting, or you might also want to model the strength of the game. Then everything depends on what you want to analyze, given the parameters. So in this scenario, I want, for example, to say, I want to use this kind of setup in order to show how the game experience in the number of turns will change depending on the parameters P and Q, which are the strength of the player, because those are parameters. In this other setup, on the other hand, I don't have parameters, because in here, everything is just dictated by the roll of the die. So I know that everything is actually 1/6. And so the thing that you could also do is just assess how many turns I will solve the game. Does that answer the question, or are there still questions about that?
So it's like pre-computed, or the probabilities are pre-computed before?
Yeah, but if you know the outcome of the roll of the die, yes. Yeah. There is actually 1/6, so it actually is given. If you don't know, which is actually the strength of the player, so that is actually a parameter. So in the code, I'm not using like symbolic reasoning in here. So whenever you're using the code base, you're instantiating P and Q potentially. And then depending on the parameters P and Q, then you're getting for each instantiation of a P and Q parameter, which is actually the XS value. So in the code, basically, for you're instantiating the class given P and Q, and then after running the code, you're getting like XS, and then you're getting XS for all the P and Q parameters that you want. And the thing that you see down below is just me manually solving the equations for x of s using the matrix, and then plotting the result using R. Yes, using R. If I recall correctly, but it should be R. No, actually it was Python and Matplotlib, so it was, yeah. And you also have the code base associated to the Python if you want, but how it was generating that. Other questions? Because I know then that might, so that's why I'm asking, because that is slightly different. But in here, I want to say what is actually the probability of winning in n turns. In here, I'm always setting a matrix, which is going to be now reflecting just not on the previous equations, but merely using the matrix that you're having. So in this scenario, I want to use like the transition matrix or the matrix itself to determine which is the probability of reaching one of the two states. So that is actually then different. The other scenario, the thing that you haven't taught, you have x of s, which was the initial state, and then you are assessing how many turns you need to take in order to reach the goal states. In here, you want to say, given the initial distribution of the initial state, so from which state you're starting from, because mathematically you could also have more than one state that you're starting from, because you might have like an initial probability distribution. But in games, you're always starting from the initial state, so you have only a very straightforward way to initialize that. Then the thing that you're doing is basically using the transition matrix to do like a random walk simulation and simulating all the possible outcomes. And then basically you're stopping after an adequate amount of iterations, whatever that means. And then basically you get the probability of reaching that state, which is actually the final state, the goal state, in a given amount of turns. So, before I explain you the mathematical contraption associated with that, do you have any intuition on how you might use a vector and a matrix to compute another vector, which is actually the probability for reaching the state in n terms, and which are the operations associated with that? I mean, that is going to be easier if you did like linear algebra, but otherwise you might still have an understanding. Let's see. An intuition on how that might be possible. So just to provide a hint, how you might compose matrices. So to have like the combination. So a matrix actually represents the transition from one state to the other. So how are you then composing matrices in order to have like the transition in two steps? That is the matrix operation that you're doing on top of the same matrix. And why? No clue? So the idea is if one matrix is actually providing you the transition from one state to the other, then if you're multiplying the two matrices, actually you're getting the probability of reaching another state in two steps. Because one matrix actually providing the probability of reaching one state in one step, then you go from state source towards state destination, and then you're combining, by multiplying the matrix, the destination to another destination. So by multiplying the matrices, then you're having the probability of reaching one state in two steps. Then you could iterate this kind of approach for all the n turns. So what is actually the probability of winning the game in n turns, basically you are multiplying the matrices n times, and then getting, for example, the probability distribution of reaching one state or the other. But that, what has that to do with the probability of winning in n turns? Well, that might be explained in this way. So you're not starting from any state, but you have like initial probability distribution. That means that all the probability of starting from one specific point is adding up to 1. And then from that state, or from those states, then you want to reach another state within the matrix. And by multiplying a vector to a matrix, you obtain another vector, which is actually the probability of reaching that in n states. So the understanding is that a vector, which is just telling you from which state you're starting from, if you are multiplying the matrix n times, you're getting the probability of getting from one state to the other in n turns. Then, if you're multiplying this vector to this other matrix, you're actually getting the probability of reaching one state in n turns. And so, that is actually the explanation, verbose way here down below. So, the probability of player 1 winning in n turns is this kind of contraption. So the thing that you're doing is, in our scenario, we are just initializing the move vector to 1 only for the cell representing the initial state, and all the other cells will be 0 because we only have one initial state. And then we're multiplying the matrix T for n times by itself. Then we're multiplying move times this matrix multiplies by itself by n times. We obtain the vector, and we are getting the probability value associated to the weight W. And that is actually what is actually computed in here. So I think that in here, that is actually something that I wanted to remark. So that just tells you, the previous analysis I was already mentioning, doesn't tell you the probability of winning of a player. It just tells that the game will stop eventually in a given amount of turns. But then you want to do a different kind of analysis, which is the probability of opponent to win depending on the strength associated of his skills summarized with a probability. So you're doing what most of the people that do not know how to use AI are doing, just model everything probabilistically with a reward function, and then you're getting something out of it. So in here, I'm not modeling the behavior of the player, the skills, the strategy that is applying. Everything is just a probability value, as the majority of the people are doing nowadays. And then in here, then I want to parameterize my analysis. So by keeping one given probability value, then I will want to say how much it will have the probability of winning the game. So that is actually what will happen if you're doing this kind of analysis, and those are actually plotted in R. Because at the very end, I'm creating just a very big CSV file, and then I'm plotting the stuff. So the thing that you have on top is actually the probability of winning of a first player. So what does that mean at the very end? So each color actually reflects the strength of the other player, and I'm just parameterizing over player 1. So the thing that is actually going to show you that is that given that this game is actually fair, then if I'm very strong, then I will have a probability of winning directly at the very beginning of the game. But then, given that a lot of things might unravel, the more the game progresses, the more the chances the other opponent will have to win the game. And so I might have like a drastic reduction of my probability of winning the game. Nevertheless, the thing that you're showing is that this kind of scenario will still hold, even then you are picking a probability of both players to be the same, so we have the equal strength. So even in this scenario, no matter how, it will be always easier to win from the very beginning of the game, because otherwise all the probabilities will build up, and so you're just decreasing the probability of winning, because maybe the chance of the other player will be greater than yours, or both players will have a very slow probability. So that will just tell you that. And the other thing that is actually affecting, by the way, as the thing that is actually stated on the slides on top, is the higher the skills of my player, P1, depending on the probability of winning of the other player, then the greater the chances of winning the game from the very beginning. Otherwise, the peak that you see in colors there will sensibly decrease with actually with the increase of the strength of the other opponent. And you could also do the same kind of analysis even for snakes and ladders, where in here I'm always winning the game, so the state that I'm aiming towards is actually the final state of the game, which is actually the state 100. So even in this scenario, then in here you see the analysis is quite different, which is I need at least 17 turns to win the game, because actually I'm assessing the way to finish the game differently. And you have like the number of moves, which are just the iterations of the matrix. But with this kind of analysis, I'm not, as I was mentioning, I'm not only getting the value associated to the average number of turns, but I'm also getting, which is actually the least case scenario, so the least amount of turns required for winning the game, and the maximum number of turns for winning the game. And then you also have like the best chance of winning the game, which is actually at 29, which is actually matching the average value that we were assessing in here, basically, without snakes and ladders. So the thing that you're getting is actually the higher probability of winning in the scenario is also matching with the average amount of turns. Yeah. So the average amount of turns of winning the game in this case are actually matching with the number of turns on which you have the greatest probability of winning the game, basically. But you're not winning the game necessarily in 29 turns. So that is actually what this plot is telling you. And the other thing that you're seeing